part of why I stick on this with the R environment, no knock on Python, is I've got over 14,000 add-on packages available. So in terms of whatever analysis, visualization, customization, whatever you need to do in terms of that, the R community is out there in a very big way. And when I see a lot of different things come up in Python, sometimes they're very often redoing other things I've seen elsewhere. Not a knock on Python, but just saying in terms of some tasks and things you may want to do with the data, we've already got a lot of other things out there. So this is me looking at one of the CRAN archives to look at the available packages. They have a lot of stuff out there in terms of task views, in terms of different types of tools and topics you might look at for something you'd want to then do with your data, some of which would be irrelevant, such as chemometrics and computational physics. But then you get other stuffs in terms of graphics, HPC, machine learning, et cetera, that provide other backends for doing this that, you know, are pretty well accessible and documented out there. So going back to where we were here. So for the most part, everybody's managed to get their first part. We got keys. And we're going to see then how do we extract data. You've already seen how to extract the basic data table. So what we want to do now is look at what are the functions in the package for subsetting and analyzing this and thinking through, well, how do I want to then analyze these sorts of data I have here in terms of finding variables or finding those relevant pieces. So there's a couple things we want to then tackle in this second tutorial. We want to look at the two different methods we've put together. Now, what I'm really doing here, and this is where I find this useful, is you're in this world where you start off with your unstructured data in basically no SQL, right? Which is already like its own, you know, you think about talking to most people and you go, yeah, I scraped a web page and classified all the metadata and then parsed all the sentences and saved all that in a NoSQL. Now, as a representation of the data, I understand what that means. And I can go back from your NoSQL entry, and I literally can build your web page back again. Okay? Now, take one of my more senior colleagues. I still have senior colleagues who do not type. You're like, they haven't retired? No, they haven't retired. I have senior colleagues who do not type. What's that? They paid people to type them for them. Let's go a generation earlier. And so their representation of what's in that web page is literally whatever they see on an iPad. They don't understand what's behind that document and all the layers and levels of information and the interconnections between that document and the other material. So imagine you've now gone through this. You've taken this giant NoSQL blob, right? You've stream processed it with the methods you've been learning here, or you've even used a dictionary-based encoder like I was talking about with Petrarch to turn this into a very rectangular, right, structured representation of the data you have. Yet you know at the end of this, the kind of query you have to do has to have an SQL-like flavor to it to dig back into this rich textual information that you've encoded. Not all of which is numeric, right? You've seen the data fields I'm talking about for the event data, right? A lot of it's still textual and you want it to remain textual. So now you've got to think about how do we get into and subset that in a way for those people who really understand the data in different ways, right? So my first one is, okay, I want to forecast and predict the data, right? Because my expertise is in time series analysis. So I want to yank out a chunk of data, right? Aggregate it, organize it by time, plot that out over time, and run with it. Because that's what I know how to do best, and that's what I was trained to do, right? So I want to get here. How do I get to this step as fast as possible? And then from there, how do I get to step 5? Right? Your other user is facing this problem. So again, jumping here, which is they care about some general area of the world and a particular type of events in this world. So let's go back to the earlier query of where do I see demonstrations and protests? And now where they want to see demonstrations and protests, and we've actually worked some on this problem, is a subset of countries. Let's say we want it to be Syria and its neighbors. Now, if you think about that, am I really worried about protests in Istanbul if I'm worried about Syria and its neighbors. No, I'm worried about a box, right? Or a certain latitude, longitude around Syria. So I want to draw a box around Syria or a contour around Syria and look at that. We've worked on more detailed ways to do that, but if you think about it, if I could do a query mechanism that builds up the elements, latitude, longitude, the geographies, we know that information in all the structured data I have here. I can go back through and use that information as part of my query. So now I'm doing something that is basically an SQL query, but I have to set it up for, remember, my modal political scientist or analyst who doesn't understand SQL. They just know they have a bunch of data elements and it's and this one, or that one. And they maybe understand that 2 or 3 levels of hierarchy deep. Right? So I don't need to teach them full-blown SQL. I just need to give them a base query mechanism that works with the data and the variables. That's what we're going to provide here. So this is someone's an expert in event data. How do I give them a powerful query mechanism? Right? So again, I go back to when we had the vignette up there, I'm praising what? I'm praising a bunch of social scientists. I'm not thanking my computer science colleagues for writing me a vignette in R. I'm thanking my social science students who've sat in my classes and actually had to do this problem. We then want to get that data back and be able to search for given variables or summarize those. So here's our second query. And I'm going to jump to the R code. We're just going to, this is here in the slides for the sake of completeness. It's easier to see in the R code. So this is our second tutorial. I like it here better because I can have it a lot bigger. Right? So our goal here, and I'm going to run through this and then we'll go through and run it. You can jump ahead of me all you want in whatever way. So this is assuming I haven't flushed my environment, so I could go through and clear my environment here by running through the session variables, or I could remove all the objects in the environment. I'm not going to do that because I have my key there. So I want to know, for given sets of my data tables in my data warehouse, what do I have available, right? So here's my summary of world broadcasts, New York Times, IQs, the real-time data, the FIBIS data, and Terrier. So I have options there in terms of which data source. From the vignette, I have the differences in their coverages that I might want to look at. So the idea here is I need to know for each of these tables which variables are in them. So remember, there's this event data community, all kind of loosely organized around those of us who talk via the Open Event Data Alliance. And we've kind of agreed there's a common set of variables that we should be extracting and including for our event data. And I'm sure you all are going to have some idea of those things after you've left here and you go back to your own respective positions. But you're all going to end up, as you work with these tools and do them, you're going to get slight tweaks or differences. Oh, one person labeled the variable this name, somebody labeled it another. And so we've got a lot of that going on here. So we want to see, well, what are those differences? Right? So notice here we've done it for the real-time data. So notice we've taken care of a lot of steps for you. Like, I'm lazy. Like, I am not going to hold the shift key. Right? So notice, I did not hold the shift key there. Actually, Zara, you didn't hold the shift key there, if I remember. But the formal name of the data set, right, is capitalized. We smoothed all that out for you. Right? So you don't have to remember to do that. So here's our table variable names for the real-time data. Right? So you see there's 25 of them. This matches the table I showed you earlier. They're in a slightly different order. Right? The event code's first, then the month, or then the source actor, then the month, then the target, but they're all there. And they match up to the earlier list, but column orderings, I can arbitrarily redo them. It doesn't really matter one way or the other. Now from those, I can then look at and compare, say, what are they in the IQs data set. And so looking at those same ones here, you see, oh, they kept track of the geography differently, right? They put in cities, districts. They spelled out Cameo code instead of just code, right? Latitude, longitude, they capitalized. They named their sources and target sectors. Source country, target country. So they've formalized this in a different way than what we did in terms of labeling those. So we labeled our, they labeled their source name for the news source by source name. When we did it in the real-time data, we've done it with, it's not the URL, which one is it here? think it's one version. One of these IDs is the one that does it. I forget. One is the internal hex ID, and then the other is the news source ID. Right, so slight differences that come up there, and we've smoothed those over within the package. Here's the same thing for the Terrier data. Those more closely match what we're doing in the real time in terms of how they're organized and the names, basically because they're derived similarly across those representations. We then have a function in here, so coming back to the main help, that gives you a random preview of data. And then it gives you back some view of this. So this allows you to say, well, what would I get back if, say, I downloaded some of this, and does it make sense for what I have? So the Terrier data, similar variable names, when we do that preview, right, we'll get this object D. So D is now in my environment. Right, so it randomly grabs 100 observations for me. Right, there's the variable names there. This is what's known as a data frame in R. It's just a rectangular file on that. If I run it without assigning it to the object, right, so just highlight and run this part of it. It's supposed to open a view for me, it doesn't. So if I do a view on D, it basically shows you, it gets this kind of spreadsheet-like data frame representation. Right, and you see, so what it's grabbed here then, all right, so here are my source actor. These are Russian actions towards the Japanese in 2005. So we have multiple ones, they involve businesses. There's their latitude, longitude's gonna be over there. These are verbal cooperation events because they're Quad Class 1. This one's 0, so that's just a comment between MDA, if I remember, is Macedonia. And you see this goes on, we get 100 entries from that. You know, so if you were trying to test, what do I get back from this? How does this fit into a workflow? This gives you a test function of, if I randomly pull back 100 observations and need to feed it into something else, how does that work then in the rest of my modeling or the exercises from that? So now we can go through and use the variable names across those particular data sets to pull out given variables or information about those, right? So I could go through now on the IQ's data and pull out information on any of my target variables, right? So this would be, you know, you're generically trying to look across and say, okay, what are different ways my target's represented within the dictionary ontology? Right, so it could be sectors. So we've recorded out there within the Cameo ontology whether or not it's a government actor, a rebel actor, an opposition actor. And we've kept track of those over different points in time, so you could trace those out. You could look at then what are the potential countries or actor names within those countries and track out what those are for those. These differ slightly because if we go back to this one on the Terrier data that we had up here, assuming it's not too far away. Yeah, here's the ones for Terrier. We only have one that matches target here. Right, there's only one variable we match to target. The others that are the subset names, that is the agent names or the actor names, we've abbreviated and we haven't used the full word target. So when we do the regular expression match to match that variable name, it only matches the one. All right, so back to the code in that second example here. When we do that, we only get the one target piece back. So we have two things here. And we've written these examples to stay a little small so that we're not all beating up on the server at the same time. You're welcome to play with this however you want. So this first one is our pull data function. So coming back here, so the pull data function is basically pull out for me a rectangular chunk of data that meets a particular criteria on a given variable. So here's the main function for this. You give it a key, which table you want, by default, a country list that you have. So that's a data object. And then you can pass it other arguments in terms of start and end. So the idea here is, okay, I know data. I want data on a particular region or set of countries of the world. I know what that list is, and I need it between date 1 and date 2. Right? So out of my data warehouse, grab me everything in that subset that's relevant. Right? Because if you think about it, that's our usual most generic thing we're presented with this kind of thing is I have a start thing that I want, I have a beginning point, I have an end point, and I have a geography. Right? And that defines kind of our base analytic piece, whether it's international relations, international conflict, civil conflict, intelligence stuff, or the rest, is that sort of thing. So our first pull here then, for our key, right, we're going to go to the real-time data. You could play with this as you wish. Right? I don't think you'll break things. Here we're passing in regular English spelled country names. You can put them in as ISO3s if you know what those are. If you misspell China and you spell it CHNIA, it's not going to give you anything, right? Because that's not going to map back into the data. But we at least have taken care of the basics of mapping this stuff if you want to use real country names back into what we have into the database in terms of ISO 2 and ISO 3, which I think is one of the more useful things we did here. You can change the dates, right? We're only going to grab, what, one day worth of data, right? You can make this extend longer. You can run it till yesterday if you'd like, right? But the dates have to go in that sort of format. So when I do that, by default, let me point out one other thing here. This is my colleague Vito DeRazio being a stickler. We have one last argument here, which is citation equals true. One of our big things and our points in this is we want you to make, at least for us on the academic user side, we want our academic user to always be able to reproduce the data and tell us where it came from. Right? So citations to the data are a key thing in our world because if someone goes back to run the query again later and it comes up different, that's a problem. But including the citation with the query allows us to track that down and make things reproducible. So when you see this, you're going to get kind of a different object back than a flat table. So that's now out. It's done the query. And if you look at my object up here, it's now a list, and it has two values. The first is the data, which is I wrote in the annotation, right? It's a data frame. The data frame is basically, it's just a rectangular object. Right, has some number of rows, 162. It's going to have 25 columns here. The other part of this is the citation. So further down the list of 2 items of pull 1 is the citation, which is a list of 9 other elements. So the way you access a list in R, right? So if I ask what is the structure of pull 1, right? So this is basically a classing mechanism in R, right? It's going to tell me it's a list of 2 things. It's a list of data and a list of citation. So if I ask it then, okay, show me what's in pull 1's first position. So you index a list here with the double hard brace, right? It's going to show me that first however many rows. If I ask for the second, it's going to give me this list of 9 elements telling me, hey, here's how to cite the data in a publication or something else. So someone could go reproduce it later. That way, whatever report or work you're doing, somewhere down the road, someone else is able to redo it or update it. So we've built that information in. So when we go to this next step here and we're subsetting data set 1, this $ says, okay, grab the first list element, which is called data, right? So again, pull 1, the first list element is named data. So that's what the $'s doing there, is it's a subsetting operator for a list. Right, so if I do that, that's now my data set 1, which just showed up in my environment of data, 162 observations, 25 variables that I can now access. So I can look at its structure, and it gives me, hey, here's all my variable names and the rest. I can go further and I can view that. And you'll notice the one thing you get with RStudio is you get partial completion. So as you start typing, it auto-completes. You just hit tab, it finishes. right? So it shows you, here's are all events that involve, right, a target country of China or Canada, right? So everything in this column should be China or Canada. And they're one of the interactors with the source and the target. So one of these has to always match one of those in what we've set up. So that would give you all their interactions over that set of months. We can pull data over a longer period of time. I tried to make sure these were all done so that when we did these, as we set everything up and it goes into the slides, or if we did, what's in the slide exactly matches what's in the code. So we stopped this instead of running it till today. It ran until we had to get the slides done the other week. So this one runs through the 20th of June, right? This gets all events between India and Pakistan as possible countries. So this one's going to be, as it says in the note, about 85,000 observations. And notice, the bigger the query, the longer it takes. This is one of our things we're trying to do on the research side is, this query isn't that much, but when you're querying back to get these 80-some thousand observations out of 2 or 3 million, now we're taking some computation time, right? Because this query is being shipped all the way to a server in Bloomington, Indiana. Right? I mean, that gets at the big data resource here on this in that piece. So, part of what we're trying to do and why the API key becomes so important to us, and it gives me the time to fill in when this is happening while the query is going on to return the data, is if we know there's certain queries like this that get done often, we can optimize this either based on dates, or we could do a hierarchy of countries and say, hey, most of the queries come on these 10 countries. Let's optimize the database to always give the queries back fastest for these 10 countries. So that's now back. That's our second pull. Right, and so here, notice all of our country codes have to involve Pakistan or India. Right, we can subset this out differently. We could say I need particular source and target combinations if necessary. Here we're basically saying, okay, I want a signal indicator on India, Pakistan. Anything involving India, Pakistan, I want to flag and have it come up, and that's what's happening here. And then you could look at, well, what are the main interactions either by event code or by country code type. So one simple thing you can do here to extend this, there's a simple cross-tabulation command called table. We'll see this again in a minute, but I'm just going to do this so you see it. So we could ask, say, what are the country codes on one axis, and this is always dangerous for an instructor to do, to stand up here and come up with an example on the fly. So I must be feeling particularly courageous today. And look at it against, say, the event codes. So what this will give me then, right, for each row, I get a country, India or Pakistan. For each column, these are each one of the cameo categories. So you see, there's a lot of general comments. There's less verbal cooperation, right? That's these categories through here. Then you get verbal conflicts, which start here in the 04s, all the way down to the material conflicts, which are down here at the end, right? And you see there's, a fair number of those, but a lot of those, it turns out, are going to be, for various reasons, false positives. The reasons they come up to be false positives a lot of times come down to a couple of things. One is we try like crazy to filter out sports stories. But it's harder than you think. And then I'm putting India, Pakistan in there. So, you don't just, the Indians don't just beat the Pakistanis at cricket.
Just the World Cup.
What?
Just the World Cup, not in the Champions Trophy.
Right on the championship, right. It says out right here. She's going to correct me on all this. So you have those sorts of issues that come up. That is, we have lots of martial verbs we use in places we shouldn't use them. And yes and no. Right. Here's my take on this. This is not much in terms of a tutorial. But it's easy to extend now, because once you understand how the pull data grabs those, all right, so let me expand this way up here. So this was like my challenge one. I said, I need to be able to pull data out so I can subset data over time so I can generate my predictions. right? Because that's how I first got into this game, right? My first entrees into doing this kind of work was some other people produced the data for me, not on a real-time basis. Like I had a static update like every 3 to 6 months, and I could live with that for my research career. But as things progressed, now we wanted to do it in real time. And so now we needed data on given countries. And so we had optimized writing the code of, okay, you gave me data back on some subset of countries and the events coded from them over a window of time. How do I derive out the data over time so I can generate my predictive model or do my learning algorithm? And so we had worked that out. And so when we first started having the code put together, this was what I wanted. And so, of course, Kate and the other grad students I cited earlier on the vignette, this was what they came back with for me. And then we figured out with Saeed's help how to extend it from our real-time data to include all the other data sets. Because our attitude was, well, why should I have to go to 5 websites and download everybody else's data when I can just put it all on my server? Right? And so we've got this common way to represent and do this. And so I tell people when you've learned the stuff you're learning in a thing like this and you go back to your own organization and you're starting to do this sort of stuff or figure out how to deploy it, don't sit and do it on your own. Because when I've sat with people to do it on my own, we get weird outcomes. Whereas if you start looking across, well, what are other people doing? You suddenly realize a lot of you are doing the same thing and it makes sense to make one data warehouse. And this wasn't a real tough one for us to do given the commonalities that we could build across the data. So this was our first attempt at this. And so we get the pull data set up that we have here. So that's one set of things, and it lets you draw that out for those. But the only subsetting we're letting you do is by country and by date. Which, as I said, in my world was all I needed. Because remember, I'm the time series forecast guy. Just give me data over countries and over time, and I can do all the rest. Because the rest of my workflow works off this. Right? So people would come to me and they'd say, hey, we want a prediction on the trend for Syria and ISIS. Okay, fine, give me the updated data, drop it in, re-estimate my models, tell me what forecast period you want, tell me what prediction error computations you want, and I could generate a trend prediction off the end of that for them each time. And that fit in the workflow that we had. What became more complicated and got us to think about more about the package, so again, this is where I go back through, how do we get to this? We start here, I have the idea. The problem is my junior colleague Vito is supervising the rest of the students, and on top of it, he's paying some of them. So now he gets to implement his idea instead of my idea. Right? And what he starts asking me to do is, no, we need to think beyond this because there's this more complicated structure to the data. Right? So this goes back to a point that I made back here in the slides, right? So here's the code we just ran and did. Right? But it goes back to a point I made back here, way back here. Here. The data are multivariate, hierarchical, and spatial. Right? And now you've seen that because you've seen the actual data. You see there are these spatial elements of the data. There's latitudes, there's longitudes, there's country names. Right? There's administrative place names, which would be where is that demonstration, where is that protest or something happening, or at least our best guess of it given what we have in the data. So his take then becomes, okay, we've got to think more about how to do these more complex queries. Right? So if we think about what we just had there, right, our other exercise would be, well, change this and just do it for Russia and Syria. Right, and get our most recent data on that. Right, so that's kind of into our next set of these. Or did that one not make it in the slides, Zara? Or in the, sorry, did it? It's in the slide, is it in the? Because here it is for Pakistan.
It's just in the slides.
It's just in the slide, okay. So what I'm going to do is take that one out of the slide. Any of you can do the rest of this, right? Right, so you've got your key, you've got the package loaded. right? So if you're not in the zoom mode on the slides, right here, I'm just going to grab this one. So I'm just going to copy and paste that back into my R script. So here I'm just going to create a new object called DT. This is going to pull all the interactions between Syria and Russia. I should show you one more trick because that was not what I wanted to do. So one thing to ask yourself when you start to do these is if you're doing a bunch of them, I'm just going to add another function around all this. So there's a function called system time. I'm just justifying this so you can see all the code in one thing. So all I've done, right, so there's a parenthesis here, and you'll see R matches it to the one, or R Studio matches it to the one here. I don't know if you can see the faint gray on there. All right, so you've got matching. What system time does, and where it becomes relevant is if you're doing big queries here against these databases, you're probably going to want to know how long they take, because if you have to rerun stuff, it's going to depend on whether you want to do it interactively or you want to store the interim product. What the system time command does is it records from the time you start the command to how long it takes to end it. Not that it's that relevant here, but I can think of some bigger queries you might end up doing against our data, particularly some of the bigger historical databases where you might want to actually test that out. This gives you a way to assess that runtime. So here it gives you basically your local user time is 1.85 seconds. System time is 0.153 seconds. Your total time is 19. So most of this is the latency back and forth to the server in Indiana. Translation, get yourself on the backbone. But you're at least able to assess what that is so you know how much time that step takes for the query. That's why I kind of put that out there. So that does basically this step. And you see it'd be easy to change out what the countries are here. You also can add countries. There's no limit. I've only been doing them for pairs. You could have 20 countries in a region you want to do. You could say, I need to cover all of Latin America. Fine, put it in the list of all the countries, right? And go ahead and run straight through those, whatever ones you need for that. So once we have those, right, we need to do that next step. That is, we want to convert these over time, right? So a time series here in this context, I'm going to go a little formal here, is I have some sequence of a variable that's indexed by time. So if you think about what I have there in terms of the event data, every row in the event data is for a fixed source target interaction at a point in time. So I could have multiple rows for the same source target interaction for a different event in the same period of time. So that's not a time series, right? That's a cross-sectional time series object where I have data on pairs of countries or source target pairs in my hierarchy at a point in time, let alone if I do it over a range of points in time, right? So now I have this hierarchy of interactions from country 1 to country 2 of particular types of interactions, a cameo code, in a time period, right? So to get to this representation, I need some aggregation of the events, right? And the example of that comes back is the first, I think it was the first one we did here. Yeah, it was in the pool 1. All right, so here's my data set 1. This was my China-Canada interactions. Right, so notice the hierarchy here, right? Either a source or a target gets me a Chinese action. One of them has to be Chinese or Canadian, right? And here they are, here's multiple on the same day, right? These are all on the 31st of October, 2017, right? So this isn't going to be that sequence of regular events that are either daily or weekly or monthly, because that's what I wanted to find out as a time series, because that's my input object for a parametric model to make a prediction for the next day, the next month, the next year. And so what I have to do is some form of aggregation on this or some further manipulation of it. So as an object by itself of, okay, here's a bunch of signal things, you've got a bunch of noise in there too. on those. And what I want to do is extract out the pure time series signal piece, or as close to it as I can get, that says, okay, here's what happened time period 1 to time period 2 to time period 3 to time period 4 for a particular set of interactions. So in that regard, I need to do a few things, right? One is I'm going to have to aggregate that data, because I've got to somehow take the fact that I have multiple observations on the same time period, the same day, the same month, and put those together, right? I either have to count them and find a frequency, I have to average their types, or something like that. I've got to have some summary measure that goes with those. The other is I have to convert dates. And someone earlier when I was saying, well, somebody does the dates 4-digit year, 2-digit month, 2-digit day versus, my 2-digit date, 2-digit month, 4-digit year, right? There's multiple ways we can do this date thing. And it gets really confusing. Here's the other one is, I need dates to be extensible, meaning I need to be able to easily go back and forth and extract out the elements for what part of a date are days, months, years, and any aggregation in between. Then imagine having to work with it where, okay, this data's resolution at best is daily, right? And this is the point I always, Saeed would tell me, no, an event has a date, it's whatever date's on the news report. No, because events time shift. They time shift because of time zones, right? So the date when it's reported in Australia is going to probably be the date that it's different than it's reported here, right? But it's the same event. You get date shifts of it takes a while for the event to get from the field. We're not even capturing that semantic problem here. Outside Mosul 3 days ago, 10 people were attacked by a rocket grenade, okay? How do I time shift that? That's not even there. So we have lots of things about dates. The other is a lot of the data we want to bring in to augment this as outside predictors and other things are on other relative date scales. So we need to be able to work across those. What's nice is the people who work with R have actually thought about this problem, and they've developed this package called XTS, or Extensible Time Series, that does this nicely. It also handles the plotting for us. So it's easy to then convert this into some temporal representation of our data. So here's the plot we're aiming for. We want to get out Russia to Syria events and be able to plot them over time. Now, there's clearly some things going on here. One of the things that comes up in the real-time data is we may be doing a really good job of capturing stuff, but the real-time thing, oops, like the server didn't do something for a couple days. All right, so this is the peril of the real-time, right, is sometimes things happen, right? Amazon Web Services does not guarantee 24/7. They still give you a percentage of 99.99 whatever. And even 99.99 whatever still means you have days you possibly could be down. Exceed and NSF are the same way with us. So you get these occasional flat spots, but for the main, we're getting what we expect here. So the question is, how do we generate this? So that's our next example here. So this is in tutorial 2. No, this is in 3.1. Sorry, my tutorials got out of order here in R. Thank you. Where am I, Zara? I'm confused.
It's with the visualization. So we are converting it first into time series and also plotting it. Yeah, right.
Right, but we're doing this, this is what then we're doing a different example. Got it. Okay, so I'm going to show you with a different thing to do the same thing. But the idea here is we've got to take that hierarchical representation and flatten it out into the time series. So we're doing a dimension reduction here for how to do that and how to do that conversion. So we're doing it here with this one then. Got it, okay. We'll talk later. So here we're going to do this. Why do I feel like I'm still missing one of these, Ara? Which one am I missing?
So we go back to the slides. Go down. Visualization.
In this one?
Next. after this, we have the example.
But it's the North Korea example, not the China, not the Russia-Syria one.
Yeah, we're doing a different example to plot the same thing.
Got it, okay. But different countries than this one. So this is illustrative. All we have to do is change the countries in the other one and you get something similar. Okay. So we're coming back here. We're going to do this part where we're going to actually go through how to do that step and do the conversion and see how that works with XTS. So that's got a couple of steps to it. Now I'm back to where I should be. Okay. And I'll show them how to switch it and do the other one too then. So there's two parts of the visualization. One is to do this over the timepiece like I was just showing and illustrating. The other is then we want to map it because the geography of this stuff turns out to be really interesting. Some of it's tied a lot to the geography of reporting. Some of it's tied to the geography of the news source and the bias in the news source. So these are things in the streaming stuff you're looking at, you're going to come across this a fair amount, particularly if you use your metadata for your geographies. And then the other is there's, as you'd expect, a whole bias towards just where population is. The problem is the events we care the most about are usually where there's the least people to actually observe them. So that's something else we've got to think about. And then we're going to want to look at this over the differences in the possible conflict types or across the pentaclasses. And so one way to think through this problem is you'd go, okay, for each source, target, and pentaclass, pull out the data. For the next source, target, pentaclass, pull out the data. For the next source, target, pentaclass, pull, no. That's not the way to do it, right? Because if you do it that way, for every source target combination you have in each pentaclass, you're doing the same analysis, because you have to flip the direction, right? You have to do source to target and target to source, right? And you have the 5 classes. So if you just think about that problem recursively, like that's not the way you want to go about it. You want to go back and treat this as a table creation database query problem and actually use that information in there to put that together. So back then to this, we're going to switch, instead of doing Russia, Syria, we're going to look at the US and North Korea. This is actually much more interesting, right? Because we're going to look at it over this period from late 2018 up through the beginning of this month. So a little more interesting. We can change the timescale back if we want. So again, we've made these tutorials so they're self-standing, right? So the idea here was you'd be able to run this straight through with your key stuck in here. So notice I'm just reinstalling the step for this. So if you hadn't run the earlier stuff, this is going to go back and check, do you have the latest version of the event data package set up, yes or no, in the course of doing that. This is not the one I'm supposed to be on. Supposed to be on that one. So again, library and key already set up. Here I'm going to pull my data. So here I've got to know that the ISO code for North Korea is PRK. If you didn't, you could put in North Korea and it will find and match those as well. This is going to get this over the relevant time blocks. So again, we're using our pull data command across those. So this is going to grab, do you know roughly, do you remember how many events are in this one? I ran this, I didn't check. How much?
75K.
Yeah. So this becomes a real kind of aggregation issue to do across these. And we want to think about different ways to go about this. So our first pass through this is as Saeed will tell you, the server setup for this is quite secure. When you ask the National Science Foundation to use their distributed computing resources, they check everything because they don't want anyone else in the system who's not authorized. And if you have the slightest security snafu, like a port not being open, or a port being open that's not supposed to, or a password not set right, or something else, they let you know very, very quickly. When we first started this up, I reached out to our base user community. I said, hey, we've started this thing. Hey, come check it out. Tell us what you can find and what you want to do. And I think within about 5 days, we had crashed everything because we had some memory security issue thing that didn't work out right, and they were very unhappy with us. But the users let me know very quickly, hey, things aren't working. Okay, so that pulls that, and you're right. There's the 75,813 on these. So the simplest thing to look at is, okay, what happens if I tabulate the dates? Because the dates are uniquely formatted. So if all I want to know is how many events were there between the US and that involve the US or North Korea on those dates, all I need is a simple tabulation of those, right? So I get that in my table function, right? So you see, it shows me I've got 119 unique dates in there, right? And it tells me how many of those. Now I can subset further into that, but a simple bar plot of that, right, uses several arguments. So the basic bar plot in R, you give it the data you want bar plotted, which here is one dimension, so it's going to plot it pretty easily in the heights. You can give it a main title. So here we're saying daily news reports on the US and North Korea from the Phoenix real-time data. We label the axes, so we get an X lab axis, a Y lab. We label that Y lab as the number of news comments or news reports that are out there. And we, for some reason, want it to be blue. So you can pick whatever color you want. We've chosen blue here for the color. All right, so now I get my bar plot that's here. You're able to check then, okay, when are there more events? How many more events are there? We see clearly there have been more events recently than there have been, over a year ago on this. We can make the table more complex if we'd like. We'll see an example of that here in a minute. Changing out the color for your colorblind boss is very easy. Right, so you can make it cyan if you want. Those who are red-green colorblind can always see cyan. So we can get those out. Now notice, this is really easy, like the earlier example, and I'm not going to save this, but I'm just going to say, where I was talking about the stuff between the Syrians. We'll see how to get that Syrian-Russian material conflict later on. It's really easy to change this. Get a whole different piece. All right, there's my same thing. All I did was change the countries. Right, now it's Syria and Russia. You see there's a much lower volume of total news reports over that. All right, so simple changes, simple processing over this. You can look at lots of different options in a pretty fast way, and you can redefine a workflow that would say, hey, maybe I have a list of countries. I want to list over pairs of countries or subsets of countries. And you can generate this sort of thing pretty quickly out the other end of it across different event types. So before I close that one, questions on kind of where we're going and what's coming through on this? So that gets the time piece. So as I said, this is the whole thing written out. You can kind of see it a little bigger here. On that, we can add, right here it is without the color, here it is with the color. So you see, you have lots of options for these graphic parameters in this. And it's one of the things that's kind of most powerful about trying to do this stuff in R is the graphing is so incredibly well developed in here, whereas I can tell the difference when I see stuff that comes out of other things. And it's nice to develop those customized kind of visual interfaces here and be able to redeploy them in a pretty nice way. So there's the version of that. I've just kind of rescaled it to fit in the slide. So here's our other one, which is we want to think through, okay, how to map these pieces. And mapping, as I've discovered, is a way trickier problem than I ever thought it was. I'm sure some of you know people at National Geospatial, so you've run across them and their issues over the years. Here we want to do is pull out data, subset it, and throw it into a map. Now, the typical way when we do this in academia is I reach out to one of my colleagues with GIS training, and I say, here's my data, here's the lat lons for it, or here's the country projections, go plot it for me. And I always think this is going to be something easy, and every time they come back and something doesn't work, right? We had one of these we were doing at one point, so we had one database of events that had been coded by humans, geolocated to the province and the city, and then given latitudes and longitudes to so many decimal places in Colombia. Then we had machine-coded data that we wanted to compare to it, where we had machine-coded the latitudes and longitudes and plotted those out. And so we overplot them on the same sets of maps. So we put one set of dots in one color and one set of dots in the other color. And all of the ones from the machines all came back within the contiguous borders of Colombia. The ones from my human-coded data did not. I appreciate the puzzled look on your face. That's the same look I had when the research assistant came to tell me this. And I'm sitting here, I'm like, why is this not lining up? Like, these are all perfectly valid points according to the research organization. These, like, literally a human stood there with a GPS at the spot of an atrocity and told me where it was. And so why don't they map up? They didn't line up because the projection system used for one set of the maps was rotated slightly differently from the projection system used for another one, meaning the perspective at which the map was made over the Earth differed. This is one of these things that only a GIS person can appreciate and love. It drives someone trying to do real analytic work on it nuts. So we want to offload as much of this problem to somebody else. So I want somebody else who's come up with how to do the mapping, but I don't want the GIS guy to get in my way because they want to argue about the projection this way versus the projection that way. Because that's not my problem that I care about. My problem is I want to see dots in places, and I want to see if the dots that I think should be in places match up with your dots in other places. So what we want to do here is think of how do I create a mapping of a particular kind of event. Here we're going to do a simple one. We're just going to look at events involving government actors as sources or targets. So this is basically saying, hey, forget what rebels are doing, forget what opposition is doing. Let's look at what governments are doing and saying to each other, right? Like, let's look at what the real, actual interstate, intergovernmental system is doing and saying to each other over a period here from 2017 to 2019. So we've got a couple things we've got to do here. One is we're going to show you how to build this up with the send query function. Because now I care about data over a couple of dimensions. The first is going to be, okay, I care about data over a time period. So we need the return times function from the package. The second part is I care about a particular expression. The event or the event code has to involve GOV, or a government actor, meaning the source agent in the data has to be a government. Now, it turns out source agents can include more than just government, right? So if you think about a health service, that's going to be a medical service that's part of a government. So it may get a med GOV code, right? Or HLH, sorry, health, HLH instead of med is media. And so I need to know how to find those subsets. And then I need to put those queries together, right? So remember, I'm trying to build up an SQL-like query for people who don't know SQL. So what are we going to do? Build the first part, the second part, and then we're going to say, okay, we're going to put this together in a list with an and. That's going to define my query. We're going to use the send query function to send that query, right? So here's the main format for the function that we're reproducing. We're going to send that query with key K to the Phoenix real-time data. There's the query, right? So key, table name, query. There's the query with the citation. We're going to get back a table of the counts by country code, and then we're going to label those. So let's run that first part. So there's where I built my queries. There's the list of them. So there we send our query. Notice when you do the send query function, what's kind of nice here, that's the API query you'd have to put together if you were going to pipe it over some other way. Right? We're just automatically building that up for you using the native R code pieces where we've given it this query information. It builds this back for us. And that's what's being shipped to the cloud server in Indiana. So again, we're waiting on these. Hey, Saeed, when are we going to make these faster? Huh? Well, but this is one of our points we're working on as a research point is how do we make these faster when we go to do them? Right? It'd be one thing if we were doing them just locally, but that doesn't really work for us as a research perspective. So that's going to come back. That object's going to be named D2. So here's D, our object from the last one. And let's see if I can open the query here. Yeah, so notice how it puts the query together as it does this. Right? Here's the query elements that feed into here. So it's got my API key that's stored in K. Then it's gathering up the date-bound information. Right? It feeds those into date 8 greater than or less than or equal to their values. Right? And then my source agents have to be a government. So there's my source agent passed in as a regex, has to equal government. And so it sends that off, and this happens to be the IP address of the event data.utdallas.edu server, or what we map to it for the queries. Is it taking too long?
Yeah.
We timed and checked all these normally, which is what you do when you do this sort of thing. And for some reason, this one's. Are you telling me I should stop it?
I was just looking which connection I connected. Did you have this?
Oh, which net? Oh, you're asking if I'm on the wrong network? No, I'm on the right one. Okay, so while that part finishes, the other part we then do with this and this is where we bring in the mapping. So this is where we use the power of R, right? We have a world map package. So we've installed that. We're going to load that in. So you've seen how to install the packages. You've got a package menu installer button at the top too. We're going to load that in. We're going to have generated here, this piece here is going to generate a table where we're going to make a table of the country codes. So that'll give us back is the country codes in a row, and then there'll be a frequency that goes with each one. So it's just a frequency table. We're going to label those. The first column in that is going to be the ISO 3 for the countries. The second one's going to be the count of the number of government events for each country. So we're then going to put that together with the map. So we have to put together the country data with the map. So this join country data to the map says, okay, what's your data? Right? It's my table of counts. The thing that's going to match back into the map is your country identifier, right? So your ISO 3 code. So you tell it that's your join code, and your name join column is that named column. Right? So they're one and the same there. I know that seems silly. Then we're going to have to give it a color palette of how to cut that, right? Because we don't want to just do all the countries that have any instance or something. We want to break them up. And so the gradations we've done on this is, okay, we want green, yellow, orange, red. So green's going to be the lowest, then yellow, then orange, then red. We're going to break these up into a cut vector based on their quantiles. So we're going to take this piece and its data, and we're going to ask for each count, what are the quantiles for each one. We're going to label those, right, into an event category list where the cuts are going to be defined by this vector we had here. Right? We're just passing those back into this cut function. So we're saying find the quantiles, then use the cut function to cut them into the 4 categories for the 4 colors. We're going to rename those because now we know what they are. So Zara must have looked up what these were for what they're going to be. So the event category is going to be low. So that's going to be our green. So it's 1 to 7.5 events. Medium, or 7.25. 7.25 to 37. So that's going to be our yellow. High is going to be our orange. Very high, which is more than 160 events. 63 events is going to be red. Then we map it. What are we mapping? The thing we put together in the data, world, and then a bunch of labelings, right? We need a map title, what time period, so that's all one title that goes with that. And then we tell it how we put the categories together. So let me jump back and see if my query worked. Nope. What's that? So if you're trying to install a package, so from up here, if you're trying to manually install a package, you've got tools, install packages. You can put the package name in there. It queries and finds it from one of the CRAN mirrors. So let me try this query again. I know what the results look like. The query just doesn't want to run. This is the map we're aiming for. And so as you see, I mean, and this is what we'd expect here, right? Countries that are more developed and have more media are going to be in the red category, right? There's going to be more coverage of government activities in those places. Whereas when you get to places that have less developed media and lower populations, I'm going to see less media reporting. It also shows media reporting bias in a nice way, right? Because look at the places that are low, they're green. You know, do I expect a lot of reports out of Greenland? No. Right? So you get that. I mean, you can play with these cut points in the course of doing it. The key thing here is you can go from data to map in a small number of steps. So that's one of the key illustrations we're trying to get in this one, assuming my query works.
It works, it just takes a really long time. Did it work for you? Yeah.
So
It didn't work for me. I mean, it worked. The colors are just wrong.
the colors are just wrong?
The interpolated colors. It wanted 8 colors.
Oh, it wanted 8? Oh, it should want 8.
What's more than 4, right? Because you need a background color plus the.
Yeah, this was one of the examples we tested, it worked, we tested, it worked, we tested, it didn't work. We worked with the other RAs. This is probably the one I'm least confident in of the ones we have here. But yes, with tweak, it will do that. We can get back to checking that, but I thought, last I ran it, it worked, but that was, yeah.
It's just sticking to, and it worked. It works, right? I reran and I had it already colored.
Okay. Okay, so I'm going to close that connection and let that one go. So this other one is now, we want to start to think through, okay, how do I actually get the dyadic data and look at that as time series? Because most often what we want in this stuff is we want directed interactions, right? That's kind of how the event data I've described are identified. It's a source interacting with a target or a target interacting with a source, right? And so we're looking at what are those pairs of relationships that are going on there. Now, it's not always what we want, right? I mean, when I know some people who were doing work on analyzing events involving ISIS, it was very easy to detect news reports involving ISIS, but trying to figure out sides was impossible, right? So you could find news reports that involved ISIS or ISIS-affiliated groups or Al-Qaeda-affiliated groups, but trying to figure out whose side anybody on was really hard to do, right? So there, when things get very asymmetric, you don't care about these dyads or pairs so much. Whereas in the kind of example I'm going to look at here, I care about the pairing of the U.S. interactions with North Korea and how that starts to play through. So here what we're going to do, and let me walk through the code, let me walk through what the code's supposed to do, and then we'll walk through what it actually does. Here we're going to go through and work with the XTX package and how it formats times and dates, and we're going to kind of do a little trick I discovered. So the first version of this, Zara did, it covered like 2 slides, I'm not trying to embarrass her, but I'm just saying, like, your initial way of doing this versus the way I'm going to teach you to do it are kind of they're not counterintuitive. It's just there's faster ways to think about how to work with dates, and I'm going to show you one of them here. So we have the event data package. We have the key. We have a pool data that's going to involve all events involving the US and North Korea, right? So here's our list of countries. It involves US and North Korea over basically 2019, right? So we're looking at the last 7 months worth of data. We're going to make a table where the first column in it's going to be the dates. So we have our date variable there. And we're going to then do our quad classes. Here's our quad classes. It's actually 5. Don't ask. It's a historical accident why 4 became 5. But they're in those categories. We want to make a time series out of that. So we're going to use the XTS package, which I'll walk you into in a minute. We're going to pull a column out of this. So D1 is going to turn out to have 5 columns, right? 1 for each of these things. And I'll show you what that looks like. There's going to be a column that counts how many neutral events. That's going to be the first column. The second column is going to be how many verbal cooperation there are, verbal conflict, material cooperation, material conflict will be the 5th column. So here I want to subset out of D1 the 5th column. So this index is in just like you'd expect for an array or a matrix. The first index are rows, the second index are columns. So if I don't put anything down for the first row, I want all the rows, comma, which column. Then I'm going to feed in a date. And here I'm going to have to get a little tricky because the dates here for this are going to be stored in the row names. So we're going to extract out the row names and tell it how they're formatted and pass those in as dates. So the XTX function by default takes in the data and then the date formats. Because we've made a table of those, the rows are unique. Right? It's just counting how many of each kind of quad classes there are for each one of the potential columns. So again, package, we can rerun all that. I don't really need to right now. See how this query goes. We've actually done this query already, so this should go fast. Am I the only one unable to do the query? Are you taking that as a good thing? I'm just trying the other network, that's all. the network you're on in those is different than the one I'm on.
What's the XPS library under?
So the easiest way to add that so in terms of installing XTS, which we probably should have included that. So if you go under here, if you go under Tools, Install Packages, you'll pick one of the CRAN repositories. You can type XTX there and then hit Install. And it'll do, see, it just populates an install.packages command. And then it'll go out and download it and its related things and install those. I'm going to try this query one more time. No, okay. So
In conclusion,
what that then does is it makes the XTS object. Here I'm going to pull out, here I am doing all of the events. What I'm going to do then is on the material conflict, I'm going to plot it out over the date and the event counts, and that's going to be US actions towards North Korea that are material conflict in 2019. You get back a plot like this, right? So if your queries run, it should reproduce one like this. And so you see you get this kind of low-level set of queries, and then as we get into the more recent months, no surprise, the query number goes up, right? So we get more and more of these different types of events coming through, and then as we get into the more recent weeks, since President Trump's come back from his travels, this stuff drops off, right? So it's tracking what you'd expect from the existing news reports or the existing stuff that's potentially out there. Okay. Since I've already crashed R once, it doesn't hurt me to restart it again. So that gets at the basic plot. So the last one of these I want to look at is, okay, once we've gotten that, and I think I need the results from the earlier one for this one, so I'm pretty sure I need to rerun that or try it again. We want to ask, okay, how do I do some sort of further analysis for this? And here I'm going to do a simple, basic sort of parametric model. So I don't know if I need to stop and entertain any questions, but if I do, let me know. What I want to do is then how do we predict that? So we've got data over time. How do we think about its prediction? And we've got two levels of things going on here. And how we want to think these through. So as I've noted, you've got space and time aspects going on in these data. And so we can think of how conflict process or how this interaction diffuses over space and over time. And so what we're really doing here is decomposing, do you have serial correlation or some relationship of units that are next to each other in space or in time? Disentangling whether that's space and whether that's time is very hard. Because if you have one, you tend to have the other. And so you get one branch of this, which I'm from, which is time series analysis, which basically says most things are related over time. Then you get people from spatial statistics, and they say, no, most things are related over space. And so what we've got to think through is what are those potential relationships? The the conflict literature behind this stuff has really only just started to explore the space part. It's really hard. It's hard here because we don't necessarily have real great geolocation when we've gone from the blob of NoSQL metadata stuff from our documents down to some derived, regularized, structured data representation of that. We just lose a lot of spatial potential information. We don't tend to lose the temporal information. And so what I want to think about as an example is, how do we work with certain straightforward parametric temporal models to do this? So this is basically me falling back on my crutch of, this is what I do most of the time, so let's do that as the example here. So what we're going to do is we're going to split this up. So for those who haven't been into signal processing or time series analysis, here's the idea. You have data. It comes in 3 parts, right? So this goes back to a theorem in signals theory by Hermann Vold in 1938, where he basically says, okay, if I observe some signal, in his case over time, I can split it in 3 parts. Some part that's deterministic, so a direct function of time or a direct function of some constants. A moving average, right? So some cyclical process that depends on past errors. And then a remaining error itself that's totally unexplainable, right? That generally in the literature is called white noise. And I can break up any sort of time series into those 3 parts. And so our goal here, and the great thing about this is an optimality type result, meaning I always can do it. Now it may be, hey, everything's deterministic, or hey, everything's a moving average, or there's nothing to explain, it's all error, but I know I can split across those 3. And what I'm hoping is I can get some combination of these 2 that does a good job, right? Because that's a regularized process I can in some way estimate or predict with some sort of model. So our goal here is, what is that decomposition across these components? Now it turns out the moving average I might need here of weighted past errors could be a really long version of this, right? So this is why, when your portfolio analyst comes to you and says, hey, I did an analysis on your retirement plan and I fit a moving average model to it, you should be very scared. Because the moving average is a weighted sum of the past errors they made in trying to predict where your 401k is supposed to go. Right, so it should scare you, right? Because it's basically saying, if I accumulate my past mistakes with some optimal weights, this is where I predict you'll be. No, I don't want to hear about your past mistakes. So what we're hoping instead is we can convert those moving averages into an autoregression where we use your past successes to predict the value tomorrow, not your past failures. So we can split this up in a couple different ways. One is I can get these deterministic components, right, which may be some function of time, some function of the logarithm of time. I may have cycles, right? So go back to your old school, think about sine and cosine waves, right? So you may have some periodicity of the data, whether it's monthly data, quarterly data, something like that, and you can fit that sort of wave to it. You could have a regression effect. So you may have some causal variables that come in there and help predict what are your future values of events or possible trend in those events. The moving averages, right, could be some past set of errors weighted together. We can approximate those with autoregressives, which are past values of the variable of interest rather than their errors in predicting those. Or I may have some other changing cycle that I have to estimate in more complicated ways, and I'm going to wave my hands on that today. So the basic model we want to think of is an autoregression. So here's my number of events or types of events today. They depend on some constant, some weight, phi, and whatever their value was yesterday. So if I think about those material conflict events between, say, the US and North Korea, right? This would be my number of them today. It would depend on some fixed level or constant. How many there were last period, last month, last year, depending on my level of aggregation. And what I need to estimate is phi, right? Where phi is going to tell me how much or what proportion of the past values predict today's values. So I need phi to be bounded between -1 and 1, otherwise the process is not stable, right? So here's simulated data when phi is 0.98. So notice when things tend to stay up, they stay up for a while. Here's a related one where phi is actually 1. This, if you let it go, will run off to -infinity, right? As it does here when it gets bigger than 1. right? Here's when phi is negative 0.6, so you get this oscillating pattern where it's up one period, it's down the next, it's up one period, it's down the next, right? So it's like playing roulette, right? You got one good throw, you got one bad throw. That would be your prediction out of that. So our basic idea here is, okay, we want to select an appropriate autoregressive model, and it turns out in R, there's automated methods for doing this and trying this out. And then we can go, okay, what's my next predicted mean number of events? And I can get out a one-step ahead prediction, a 12-step ahead prediction, which is what we're going to look at here. And here we're going to look at it on India-Pakistan relations. So we're going to end up blowing up the example I was just running. Yeah, I'm getting timeouts on the server. Saeed just came back in the room. He doesn't like hearing that from me. So here we're pulling these events for India and Pakistan, right? So we gave it our list of actors for India and Pakistan here. Yeah, I'm not getting data today. So this is one way when you get error messages in R, you can go back and use a traceback command and it'll tell you where that was, right? So here it's giving me a warning message. And
It's your internet connection.
it's basically I got a connection that's not working is what you're telling me?
Oh, I haven't gotten that one a lot, that unused connection rate. Doesn't seem to bother me.
Well, here, wait a minute. The thing is, it's not giving me back the object.
I think that's any query that you stop.
Yeah, it's given that same error message.
Yeah. I think so we've all stopped a bunch of queries and kind of closed out as the server wants to start.
We've starved the server for resources because we've done so many queries in the Right, but remember, Zara, we have 20 people in here doing queries at once, plus they're running multiple versions of them. And so what's happened is we've timed this piece out. I mean, I'll run it one more time. So here's the query code for this. Here we again make a table of the dates, the quad classes. The head function basically says, show me the first 5 or 6 rows. We then make sure the XTS package is there. As before, we're generating a material conflict measure for our 5th column, right, which is our material conflict in that. The dates are formatted from the row names, right? So we're extracting out the row names argument from the table here that has a year, month, day format. Then we plot that out. So we'll get a plot that looks like this one, right? So this covers the relevant time period from 2018 to the end of June 2019, right? And so you see we've got, here's that period where we're having trouble getting data again, right? But you see we've got this process that comes along here. Now, when we want to diagnose that process, yeah, we're going to let that part go. So we've hit our limit on queries that the server will accept. I'm going to run that one too. So once we've gotten that, we then need to diagnose this time series. And so there's 2 ways we do this. One is an autocorrelation function. The other is a partial autocorrelation function. So an autocorrelation function asks, okay, how correlated am I with the data the time period before I am? Then it asks how correlated am I 2 time periods before that, then 3 time periods before that, then 4 time periods before that. Right, so data that are correlated, say, only 1 time period back, All right, so here I'm just going to make 100 observations like this. All right, so there's my autoregressive data with a first order lag. So that's in my back in my slide when I'm estimating phi here. What I'm doing here is I'm giving you data where I said, okay, phi here is 0.7, right? So now I want to know, well, what are the partial correlations in that? Right, so I want to know what are the correlation estimates 1 period back, 2 periods back, 3 periods back, k periods back. So that gets me this piece, right? So I asked the autocorrelation of x there, and it plots those out. And right, it shows me the first ones, you're always perfectly correlated with yourself. 1 period, right? Where are you? I'm perfectly correlated with where I am right now. 1 period back, I'm less correlated. That's the 0.7. They decay down from there. Now what happens though is this one here doesn't account for the correlation there. And this one here didn't account for the previous 2 correlations estimated. So we have to account for those interim correlations. That's what the partial autocorrelation function does. It reads that one off and starts at 1 and says, this is 0.7, trails off after that. So we use these as diagnostic tools to determine what possible autoregressive model to fit. So we could do that, but then you got to learn a lot of time series and you got to read the tea leaves. Right? So this is when you talk to the signal process guys, this is what they're spending their time doing. Right? They're trying to find some version of how to read those tea leaves for that. The other way out of this, and I'm just going to work with my simulated data here then from this point out, is I actually have an autoregressive model that'll take that data in and will do optimal model selection for me and choose among the possible models because it's going to try, what if I only include 1 period of history, 2 periods of history, 3 periods of history, k periods of history. And it's going to use an optimal fit measure called an AKK information criteria, an AIC, and it's going to minimize that criteria. So it's going to pick the best model that makes that fit criteria as small as possible. So this is like you pick your tuning parameters in the machine learning model, and then on the other side you have some fit statistic, and you're always trading off how much tuning you've got versus what the fit measure is. Same thing, right? Except this is all parametric, and a lot of that stuff's non-parametric or semi-parametric. When I do that here, right, it goes through, this is the optimal thing. It selects, this is the same as the other options I have in the other code. It selects a 1 lag model, so it gives me 1 coefficient back. If I ask for a summary of that, I don't remember if this gives me a summary or not. We're going to see if it gives me what I'm expecting. No, it doesn't. So when I do that, it's basically giving me back a 1 order lag model, and it says the variance of the prediction error is going to be 0.82. Right? I can try that with other specifications, which is what we have in the other examples here. Right? So that's the equivalent of doing what's in this step. Right? So this, when I did it with the actual data for the Pakistani stuff, basically comes back with a 3 lag model. The other would be to use an autoregressive integrated moving average model where I tell it the model order. So here's one where I tell it I want a 1 lag model. Here I tell it I want a 3, and it'll come back and tell me model 2 is better than model 1. Right? So in this sense, I've got a way to optimally engage in those predictions with, in this case, a parametric model that goes through and sets this up and gets me the final analytic pieces. So here's what that output would look like if I had the data, right? So here it fits it.
Do you want to use mine?
Is yours working?
Yeah, it works.
Okay.
Yeah, there's something wrong with it.
There's something wrong with that.
That never happened. So it's-
Yeah, but you don't have an HDMI input. See, if you'd like to see them on here, no. And I don't have an adapter today. That's okay. I've got the output. I can show the output I have.
You have USB-C on that? I have a HDMI.
Oh, yeah, that one.
You have the USB-C?
Sure.
Except, where is it? Yes, we're good.
No, this is for, no, sorry.
Oh, you don't have to use it?
I do, but it's the other one.
Oh, that's Thunderbolt.
Yeah. Sorry, Dr. Britt.
That's okay. We'll work with what we got here. Let's just run with what we got. So here's where this was the code that runs and does the optimal lag selection model, right? So AIC is true. It picks a 3-lag model. It estimates an intercept of negative 0.5, variance estimate of 500. Here it is with the 1-lag model, right? So again, we get an overall fit. The variance estimate's 500 there. The variance estimate's 538 here, so that model's worse. This model goes on. It comes out better. It's the same estimate and the same result as this one right here. Right, so they're barely popping through at the bottom. I can see them here and I can see them on mine, but they're not on the slide. Okay. We then can go through for those various models and generate a prediction, right? So here was my autoregressive model. So I can say I want to predict those 12 periods ahead. So it's literally a simple out-of-sample prediction model where it generates the predictions. So notice it starts at 28 events, 37, 34, because it's cyclical. 37, but you notice it's climbing. So 12 periods out, it goes from 28 to 43, right? So you definitely have an upward trend here in the number of events. So if you were considering these to be, some event of interest for you, you're saying, hey, this is getting worse. We're gonna be 15 more events on average 12 periods from now than what we were before, right? That, depending on the nature of the event, this is material conflict, that's bad. At least in our classification of this. Here's the standard errors on that. So notice you're still within a standard error, right? So yeah, you definitely have this, but you're within a standard error because you started with a standard error of 22 units around that, meaning you could have gone from, 1 standard deviation above or below, if you're from 6 to 40, or from 6 to 50, right? So this is clearly within that, especially when it has a standard error of 25. So you can go back and plot this out and you get a nice plot of the standard error. And you'll say, yeah, we have a trend, but it's not anything we'd say is statistically significant coming through on that. Whether you apply this kind of model or something else, the point goes through is you're able to take your event data from the glob, the no SQL, unstructured, get the structured information, carry it through to other summaries that then convey that information. Because that's the big problem we run across working in these areas of thinking about big data and international relations, big data, national security, in big data and streams, is how do we reduce down what's happening in that stream to something intelligible, right? And where Lautefer and I work in these areas are very different in some ways, but they're very complementary in others. That's kind of why we've tried to put this together the way we have. So let me summarize and take some last questions here as we're down to our last few minutes. One is, we've gone through and I've kind of given you the political science view of event data. When I first got into this, it turns out this phrase is used in different ways in lots of areas. So I've given you kind of the international relations, political conflict version of it, but there's a whole other use of this stuff in network detection, right? So I know when I've gone out, like a Google Scholar query on this, puts me in a weird world when I go looking for some of these things. But I hope I've gotten you to understand kind of how we think about this and how what you're doing and the stuff can interface back in with what's going on in some of the academic community and the contributions we're making here. Because I think at least part of what we've been able to do and what we've thought seriously about is as we put this stuff together, how do we make it absolutely usable to as many people as possible, right? Because we want to scale this out, whether it's letting people work with it in Python, whether they work with it in R, whether we are able to just dump out flat files for them of the derived, structured data, that we've gotten. We can do that in different ways. I think the other thing in here, and I disagreed with my colleagues when we first did it, knowing and having and controlling the access of who's getting into the stream where and when is important, because if you're trying to do different analyses of the stream of data, you've got to do it in a way that's reproducible. And that's one thing we've thought a lot about with this R package is different people are going to jump into working with or accessing your data stream if you're producing one at different points. And depending when they jump in, they may find some very anomalous, weird things. We've had this happen as we produce some of the event data streams for the political applications and thinking through how to do those. We've had some people engage in some serious use and abuse of what we've done. The great examples have been around people trying to query out protests. It turned out at one point, people were looking at protests and mass atrocities in some of our earlier data. And it was around the time of the Boko Haram attacks on the girls in Chibok. And so you can imagine when you were looking at the streaming news reports around that event, whether it was the atrocity of the girls being kidnapped, the atrocities of the girls being raped, the atrocity of people protesting the atrocity, protests around that event, like you're just looking at the streams coming in around that event, they're really a mess. Now, as an analyst who understands that stream coming in, I knew what a mess they were. But the reporter who grabbed the data from the streams that we had processed and originally made available didn't understand how messy and noisy they were. So this is part of my irony in you guys gathering streaming data from The Guardian, because she happened to be a reporter for The Guardian and ran a story in The Guardian about how awful things were and about all this news coverage and claiming there were many, many more events than were actually reported because she believed all the duplication in the streams. Right? And that duplication in the streams is really common because if you're only tracking a small number of news wires or news reports, you find this problem all the time. Report 1, there's a bombing. Report 2, same event, there's a bombing, 6 people dead. Report 3, there was a bombing, 6 people dead, 4 injured. Now, if you just count bombings in space and time, you just got, what, 3 or 4 reports. They're all the same event. Right? So that's one of the perils we run into here, and it's why you need to have ways to dig into the data. It can't just be somebody's got to know how to run the right script and do the right deduplications or the right comparisons to do it. We've got to have these sort of open APIs to get at the data and stuff. What I found is most useful and why we put so much effort into this and the illustrations of it is I want to be able to take this in the classroom. Right? And I want you to be able to take it back and show other people, hey, we can do this sort of thing. It wouldn't be hard to pivot what we've done with this R package. It's on GitHub. It wouldn't be hard to pivot it to another application in what's there. And I know if someone came to me and said, hey, we've got this sort of thing, we want to do this, I'd certainly be willing to try and pitch in and help do it. And I've got our team here willing to help do it too. So self-advertising there. But the other, I think, thing is important is we've got to reduce down what we get out of these streams into things that the consumers want from us, right? Whether it's me on the research side trying to show people, hey, these are the patterns that are out there. These are the inferences we can make. These are the inferences we can't make. This is the predictions we can do. This is what the predictions we can't do. And that means we've got to be able to convert and think about the data in different ways. And the visualization is the key part of that all the way through, whether it's the Kibana stuff they were showing you earlier, or even the simple time series and spatial representations that I've been trying to do here. So with that, do we have any questions?
We can easily combine this data set or merge it with any data set which has country names, right?
Correct. The other, just as a further thing, because I have never seen anyone do this. I'm not saying it can't be done in Python. It's just again, I don't have a knock on Python. It's just one of these things that's been thought of nicely by some of the political scientists and social scientists who've contributed a lot to R. How do we put together lots of disparate data? And one of the great examples of this, we had the time discussion earlier, is countries, right? And representing countries, country names, and different ways to do that. The people who maintain this country code package have really gone through and thought about how to do this and realize country names are not static. They change over time. And they've actually thought this through. If I'm having to track countries over space and over time, how do I do that and keep the data interconnected over the right dates? Right? So if you're really trying to work with historical data and bring it back to contemporaneous data, how do you do those? How do you make those challenges out and do that And I would note this package for this, yeah, the current author is Vincent Errol Bundock. I know some of the other people he's worked with, and they put a lot of thinking into this and how it's done, and they know a lot of people rely on it, so they take a lot of feedback on it. But what's nice about it is it solves those mapping problems in this. And what do I mean by that? Well, here's all the different country mappings they'll deal with. So names in English, names in German, correlates of war, character or numeric, ECB, Eurostat, global administrative unit layers. Two political scientists, Christian Gladich and Mike Ward, have built some data sets that have different representations of them. The IMF, the IOC, I mean, you're like, wait a minute, there's that many? Yeah, there's that many different ways to think about just representing country names in codes form. And so you're right, we're actually plugged back in with this. And so you're right, I know you're working on some stuff with some of this conflict data and some public health data and trying to make those comparisons and get it lined up. You need this functionality, and we've built that in.
So what countries do you consider Abkhazia, South Ossetia, Crimea to be part of for figuring these things out?
Well, there you're down to which one of these recognizes them. I take the point as given, right? It's when I've been asked before, how do you predict nation-state conflict between the Israelis and Palestinians? That presents its own challenges because the Palestinians aren't in most of the databases.
And then when Yugoslavia broke up into the 7 countries back in 91, if you do...
So that actually, if I'm thinking back into our data for that, so the Terrier data is where that's going to be covered because that's going to cover the historical time period of the conflict in the former Yugoslavia, if that's what you were looking for.
So no, actually it was a matter of when you do, so say you're trying to find out something was split in Macedonia, which didn't exist prior to 91, except as a state of Yugoslavia.
Mm-hmm.
How would a query that bridges across, say, 1985 to 1995, how would it handle that?
This is getting a little afield of the lecture, but it gets at some other things in our event. It's not in that one. This gets at one of the things we've actually tried to handle in the event data, so I'm just trying to see if I have an example of this. So this is one of the things we're actually able to do and capture with the parameterized event data, where we're working with the fixed dictionaries and Petrarch and Petrarch's successors, is say we're able to map in changes in actors or changes in things involving countries. So here's part of our entries for Afghanistan. And so what you'll see on these entries, I need the laser pointer for this, sorry, is when we're encoding information about actors, which encodes information about the countries they're then affiliated with, right? We will record in data information about what that actor's role is within a given government. So this is part of the human side of the dictionary development. This is the really expensive side that we've actually tried to minimize the costs on as much as possible, because this is the thing, when we're trying to develop these data, this is the big cost function of me having to hire people who have the expertise in these things to do the kind of splits like you're asking me to do. So here's a whole bunch of Afghan actors, and you notice these are on a 2-digit year, 2-digit month, 2-digit day format. So here's, Ahmed, Mokbel, Zarar. So he's in the Afghan government from this period in 05 to this period in 06. Then he's back in the government from this period in 07 to this period in 08. And then he's back in government as a police actor after 2010. So we capture your role in and out. And the great example of this is if you think of Israeli politics, think about all the roles Ariel Sharon ever held in the Israeli government. So the Ariel Sharon entry goes on for pages to capture all this. So we can capture some of those differences over time and over space within actors and within countries in this format. This is incredibly human intensive to put together. right? And so many of the tools you're being taught are how do we find ways around this where yes, we can get that human information in there, but it's not part of having to be in the weeds updated like this. But even this is part of the dictionary information that's on our GitHub site. So you'd be able to go there and see those and see what we've done with them. Well, if we've got no other questions, I'll let things go for today. Thanks, everybody.